geology lectures. And so I've been doing this for about a year now, picked up a thing or two about Grand Canyon, but it really helps having a boss who is a geologist. My boss, Canyon Dave, spent many years living and working out here at Grand Canyon, studying the rocks and strata. And that's all a geologist does, really. He looks at rocks, then he thinks about them. So just imagine what kind of work you can get, looking and thinking about rocks. Pretty good job if you can get it. The first part of my talk is going to be talking about rocks, kind of taking you guys back to fourth grade, back to that elementary level, and we talk about how rocks form, what kind of rocks we have here on Earth, and how they change. That way when I tell the story of the Grand Canyon, tell you how all of this formed, you guys can visualize it. You'll see it happening right in front of your eyes. So that's going to be the first part of my talk. So I'll be going over some technical terms, some processes you might not have heard of in a long time, but feel free to shout out any questions, interrupt me at any point if you guys have any, and we'll talk about it. No worries. I'm going to start you guys off with a really hard technical term, and I've got a wonderful example right here. In fact, I've got many, but this is one of my favorites. This, ladies and gentlemen, in technical terms, is a rock. A rock is an aggregate of minerals. It means, in geology terms, it's just an aggregate of minerals. It's a bunch of minerals packed together into a solid form. And we've got three kinds of rocks here on Earth. We've got some ignorant rocks, some moronic rocks, and some sedentary rocks. Wait a second. Sorry. I'm thinking of my roommates. Gotta think of rocks. Gotta think of rocks. Igneous, metamorphic, sedimentary. Those are the three kinds of rocks we have here on planet Earth. And they go through what's called the rock cycle. Rocks are always changing. They're always going through this state of change. Whether they're eroding, or melting, or forming from molten rock or sediment, or from old rock. Rocks are always in a state of change. Even by sitting on these rocks here in this amphitheater, you guys are helping change those rocks. You're helping erode them away just a little bit just by sitting on them. Very, very, very slow change happens to rocks. Sometimes we can't even see it or measure it in our lifespan, but they're always changing. The first rock I like to talk about are the igneous rocks, because they're kind of the first rocks. They started off in a molten state. They started off as magma or lava. Only difference between magma and lava is their location, where they're at. Magma's underground, lava is on the surface. It's come out of that volcano. But both can cool down and solidify and become stone. And this right here, this is granite, one of my igneous rock examples. Granite is a magma rock. Sometimes that magma's working its way up towards the surface, doesn't quite get there, and so that magma starts slowing down underground, and then it cools and solidifies very, very slowly. There's still a lot of heat underground, so it takes a long time for granite to form. Granite's really pretty, lots of different colors, and coming from the different minerals. In fact, these minerals are pretty easy to see. We can spot the individual minerals that make up granite, and that's because they form these really, really large crystals that interlock really, really tightly, so that we have these really hard, dense rocks, but we can see the individual minerals inside of it. Most of our Grand Canyon granite looks like this. Very, very, very pink, almost orange or red. Lots of iron and feldspar inside of this granite. That is the granite, or Zoroaster granite. Lots and lots of that stuff of that minerals inside of their iron and feldspar to give off that red color. Got a little bit of that in here, but a little bit more quartz, silica, mica, looks like a little angelite. So lots and lots of minerals going on inside of granite. I'm going to start passing rocks around. I'm going to pass one up here, and I'm going to start the other one up over here on this row. If you guys are looking for our granite, it's down at the bottom of Grand Canyon, one of our basement rocks in the Vishnu complex. It's going to be the pinkish, light-colored stuff streaking through the really, really dark stuff down there. That dark stuff down there, that is a different rock. That is a metamorphic rock. And metamorphic rocks started out as rocks. They could start out as any kind of rocks. They could start out as granite. They could start out as sandstone or limestone or shale. Any kind of rock. But these rocks get forced deep underground. Lots of heat and pressure down there. Not enough heat to turn that rock back into magma, not to melt it, but there's enough heat, enough pressure, and it's going to start working on that rock, start rearranging minerals, molecules get broken down into their base elements, then new minerals form. And after a few million years of this pressure cooking, it takes a long time, but after a long time of that pressure cooking, we end up with metamorphic rock. And the metamorphic rock down at the bottom of Grand Canyon is schist. Be careful how you say that. Just down at the bottom of Grand Canyon. We've got three kinds, Vishnu, Rama, and Brahma. This is two examples of Vishnu schist. What's really cool about these is that when you look really closely at them, they've got these horizontal lines or layers kind of going on inside of them. That's what we call foliation. That's the evidence of the pressure that happened to this rock. over time, that rock gets squeezed by all this pressure deep underground, and it kind of gets folded and squished together. Imagine someone playing an accordion, and then when they push that accordion in, you get those tight parallel lines. That's the kind of thing we got going on here, the foliation of the rock, that squished effect. Starting one over here, and I'm going to start one down over this way. The two other rocks I unfortunately do not have examples of are basalt and gneiss. Basalt, one of our igneous, gneiss, one of our metamorphic rocks. Gneiss is actually metamorphosed granite. Just imagine those granites that are being passed around being squished and have that layered foliated look. Basalt, that's lava rock. Lava on the surface cools off really, really quickly, gives you that dense black rock. Basalt, generally low in silica content, so it moves really, really quickly and cools off really quickly as well. The next kind of rock are all the other rocks we have out here at Grand Canyon. Everything on top of the schist and granite down at the bottom of Grand Canyon. Those rocks are our sedimentary rocks. And of course, sedimentary rocks came from sediment, loose stuff like sand, silt, dirt, mud, clay. Anything loose that can be deposited into an area, over time it can lithify. It'll lithify and become stone. Now that lithification process is all dependent upon water. Have you guys ever boiled a pot of water, then you get that white ring on the top? Yeah, it's all the minerals inside of your water. Calcium, magnesium, manganese, lots of minerals inside of water. But when water trickles underground, it goes deeper and deeper down, following gravity. Eventually it goes through layers of sediment that are so tight, so compact, that the water keeps going down, but it leaves the minerals inside it behind. They get strained out by all that really, really tight sediment. And then we end up with our sedimentary rocks, because those minerals will act as a glue or a cement, fusing all those pieces together to give us stone. My first example, sandstone. Once was sand, now it's stone. And if it erodes away, it becomes sand again. This, the Coconino Sandstone. Layer number 3, the white cliff out there near the top. Yeah, formed 260 to 270 million years ago or so. It formed this huge, huge desert out here. Like the Sahara in Africa, all those sand dunes lithified over time as water. Every now and then you'd get water in that desert and it'd trickle down, start lithifying those sand dunes. You can even go up to the Coconino Sandstone if you're hiking down into the canyon, and you can see how those dunes would have looked, the layers of those dunes. They were preserved so well, so tight. So that's our Coconino Sandstone. Nice and smooth. In a desert, wind is constantly blowing that sand around, so it gets smaller and smaller. We end up with a nice, smooth, fine-grained sandstone. This is the Tapete Sandstone. A little rougher, a little coarser, more jagged. The Tapetes is your number 9 layer. Almost all the way down at the bottom, sits right on top of the schist and the granite. Forms an unconformity. The rock, the schist and granite at the bottom and the Tapete Sandstone are separated by almost 1 billion years worth of time. So there's this big gap in geologic history that's missing between the Tapete Sandstone, that brown cliff, all the way down at the bottom, and all the schist and granite underneath it. So that Tapete Sandstone, that rough one, that was created in a beach environment. We had a beach over this whole region long, long before the Coconino Sandstone, that Coconino Desert, and long before that, that Tapete Sandstone formed. As the seashore encroached over the land, or as the ocean encroached over the land, the seashore followed right along with it and left all that beach sand that lithified into the Tapetes. Beach sand does not break down quite as quickly as desert sand. Water kind of acts as a cushion, so it churns around a lot in that water, but doesn't really make itself any smaller. Sandstone and limestone, a little bit more resistant to erosion out here than other rocks. So they're going to form our cliffs and our ledges out here, our vertical shear face cliffs and ledges. That's because softer rock underneath them will erode away first. That undermines those harder layers, and then gravity takes over, takes big chunks of these rocks down, big blocks of them fall off, leave us our vertical cliff faces. All of our slopes here at Grand Canyon, all of those are layers of shale for the most part. Layers of shale. Pretty much just dried up mud and clay. That's all this stuff is. Dried up mud and clay. Lithified, tightly packed grains of mud. This is the Hermit Shale. Came from a river delta or swampy environment. Before the Coconino Sandstone era, before that desert was here, we had that river delta and swamp, and that put down the Hermit Shale. Very red rock, and that's because lots of iron inside of it. When that iron is exposed to the atmosphere, it gains an oxygen. It's called oxidization, and it gains that oxygen and basically becomes another mineral, becomes hematite. It's rust. That's all it is. This rock is rusty because of all the iron inside of it. Then we got that green shale, the Bright Angel Shale, layer number 8 down at the bottom. Or not quite down at the bottom, it's that flat green platform above the Tapete and above the Vishnu complex. So you're getting close to the bottom, but not quite all the way down there. Nice and green because of a mineral called glauconite. Lots of glauconite inside of this rock to make it green. Lots of good fossils inside of the Bright Angel Shale, including trilobites and worms and all kinds of other little sea creatures when this Bright Angel Shale was laid down offshore in that environment right after the Tapetes was laid down. So just imagine that kind of offshore shallow sea environment with lots of mud, lots of life going on. Lots of trilobites. Those are the first creatures in the fossil record to have eyes, so really important in the fossil record. The Bright Angel Shale is also really cool because it forms an aquiclude out here at Grand Canyon. It's got a pretty high clay content, and so it's hard for water to get through it. It's hard for water to permeate or penetrate this rock. So when groundwater seeps underground, going deeper and deeper down, it hits that Bright Angel Shale, can't go any deeper. That's when it starts going horizontally, and we get our springs and seeps out here. Water gushing from the sides of the cliff and coming right out of the right out from underground. Oh, thank you, sir. Lots of shale creates aquicludes. The Hermit Shale in some areas even creates an aquiclude every now and then, but not quite as extensive as the Bright Angel Shale. And I've got one more rock to show you guys. Limestone! Limestone. You guys are sitting on one layer of limestone, the Kaibab limestone, that's this guy here. And this is the Redwall limestone. That's the really, really big red cliff halfway down the canyon. One of our thickest sedimentary rock layers. Now limestone is interesting because it always forms underwater in aquatic environments. Its main ingredient is seashells. Seashells make up limestone. Let me tell you guys a quick story of how that happens. All starts with a little drop of rainwater falling out of the sky, little raindrops falling, falling, falling. As that raindrop falls, it pulls in some carbon dioxide from the atmosphere, gets inside that water. So now we've got all these raindrops, they hit the ocean, now the ocean's got all this carbon dioxide. Well, there's some critters down there that can use that. They'll take the carbon dioxide out of the water, they'll take some calcium out of the water, put it together, get calcium carbonate. That's what they'll use to make a seashell. Well, they die, and of course their shells fall and sink to the bottom of the ocean. And we get this limey, silty layer of mud forming at the bottom of the ocean when all these seashells start getting broken up, and it keeps piling on over time. Well, geologists have a technical term for that. We call that stuff at the bottom of the ocean ooze. Ooze at the bottom of the ocean. It keeps piling up and piling up until it lithifies and gives us limestone. The Kaibab limestone, once again, you guys are sitting on it, our youngest sedimentary rock layer out here at Grand Canyon. And of course the Redwall limestone. Now the Redwall limestone is not really red, it's this color, kind of an off greenish, off gray, but it looks red, right? That's a pretty red cliff. That's because it sits underneath the Supai group and the Hermit Shale. Those are layers of shale and sandstone that have lots and lots of iron, so they put off that red color, they rust. Well, when it rains, they bleed. That color gets washed down, paints the cliff below it red. So instead of getting this color on the cliff face, we get this color. Very, very red. Alrighty, so those are the rocks you find out here at Grand Canyon. Now I can tell you guys how they got here, how all of this